In today's video, we are going to create a resistance meter, ohm meter with the help of Raspberry Pi in Python programming. And the sensor we are using is 16-bit ADC, which is ADS1115. So this is a sensor which communicate with the Raspberry Pi through I2c protocol. So we connect the VDD with the 3.3 volt SCL and SDA to the respective pins of Raspberry Pi, and then we connect over respective voltage divider onto the one of the four channels of the ADC. Coming back to the SSH console of my Raspberry Pi, what I'm going to do, I'm going to sudo raspi config to enable the interfacing option, and inside that I have to enable the I2c interface. Would you like the ARM I2c interface to be enabled? Yes. And when our I2c interface is enabled, we are done. Then we will interface like this with the help of the circuit diagram, and we go back and we will say I2c detect and -y1 command. This will give the list of the connected devices onto the I2c pins. The default address of the ADC is 48 in hexadecimal, and this 57 is for max 3102 pulse oximeter sensor, which I showed you in previous video. If you haven't checked that video, you can go to the link and see that video. So here we will see this address of our ADS1115 ADC. So it means our ADC is connected. This is a verification that our ADC is connected. Now we can come to our Python and we can import a few libraries to help us inside our programming. So there are the libraries which we need to install for our ADC reading, and the library which we are using is sudo pip3 install adafruit -circuitpython -ads1x15, and we need to pass the break system packages command so that this will be installed inside our system packages. So we are using a CircuitPython library. We have another option to use without this CircuitPython code. So there is another variant of from Adafruit. You can choose any variant you want, but in this programming, in this video tutorial, I'm going to use the CircuitPython version. So once done, let's open up our code, which I previously write sudo nano adc_test01.py. So what here I am doing, I imported the board, then bus IO, then the over library of ADS1115 as ADS, and then I imported a function of analog in. Then I imported the time. First of all, I created the I2c bus with the help of SCL and SDA pins. Then I initialized my ADC. Then I changed the channel with the help of channel 3. ADS.P3 indicates that I'm going to read the channel 3. So this is the basic configuration I need to do to read the ADC. Then I have created a function of read average voltages because the reading is too fast. I created a average function. What this function will do, it will create a values, voltages and start time. Then I implemented unless it is a less than the start time, which is automatically a sample time is 1 second. So it will sample almost 1 second. And then it will append the values of the channel raw values and the voltages. These two values will be returned from the library. So basically our library, which is reading through the ADS1115 ADC, it is basically returning two values. One is the actual raw value of the ADC of a 12-bit resolution, and second is the actual voltages being read. Then if we are adding 0.1 second delay, then we are just calculating the average value of an average voltage, and we are returning this to from this function as a tuple like this. So how to use this? We simply read the average values and then we print it out. So let's come out, clear it, and run this code ADC test01.py. So here you will see at every 1 second, it will printing the average raw value of the ADC and the voltages. I have added a 470K pull-up resistor uh, on the A and 3 pin. Then to measure the resistor which need to be calculated, we will connect that resistor to the ADC channel 3 pin and a ground. So that how it will become a voltage divider, and with the help of simple voltage divider formula, we are able to read the actual resistor value. So let's come to the over next code, which will read the ohm measurement of the resistor and will return it as well. So this is the code test2, and inside that almost the function is very similar. Rather, we implemented one more function to calculate the resistor. This function is calculating if the average voltage is greater than Vin equal to, it means that reading is invalid, which means it is too high. And if it is less than equal to 0, it means invalid reading voltage is too low. These are two the edge cases which we are handling. Otherwise, this is the average voltage divider formula. And to measure the resistor, what we are doing, we are R1 multiplied by average voltage divided by V in minus average voltage. So from this formula, we will calculate the resistance to be measured, and we will return this R2 resistor. And inside a while loop, what we are doing, we are simply reading the average value and average voltage, and then we are calculating the resistor based on this average voltage. And after that, we are just printing it out like this. So let's come out from this loop and see how it will work. So we will simply run it Python ADC test02.py. So this will return the measured resistor. For now it is open, so it is returning very high resistor, which is open resistor. It is just returning a very high value. So it is basically 7768 K resistor almost. So let's say I add one resistor to the terminals and wait for the value to be changed. I am putting it manually with the hand, so my hand resistor will also be added. So it is saying 325.43K ohm resistor. So yes, I attach the 330K value resistor, and it is calculating the resistor very accurately. Now we will test with the 220K resistor. Let's add this with the 220K, and let's figure it out if it is calculating the value accurately or not. Okay, as you can see, it is giving pretty much a closer value, which is 240K resistor. So 220K with the which is 10% tolerance. And finally, let's test it with the 1K resistor. We have tested with the higher resistor, then we are just simply calculating the low value resistor, which is 1K. And as you can see, it is returning almost 1K resistor, right? Because the tolerance ratio of the resistor is a golden band. So it means that it is returning very accurate resistor measurement. So that's how we'll create a resistor measurement from the Raspberry Pi ohm meter. And that's all for today's video. We'll close this by pressing the Ctrl+C button.